Hello, statisticians. In this video, I'm going to cover section 8.3, where we get into estimating a population mean. So what we're going to see here is checking the random 10% and not the large counts condition, but something else because we're dealing with a quantitative variable. We're going to actually introduce a whole different type of distribution, and then we're going to get into the four-step process for creating a confidence interval for a mean. So here's the problem. When we try to create a confidence interval for a sample mean or for a population mean, we would need the population standard deviation. We don't have the population standard deviation. That becomes a problem. So what we have to do is we have to estimate the population standard deviation. And what we use in place of that is this right here, the sample standard deviation. So as a result, we're going to get some increased variability because now we have another estimate. We're estimating the population mean and now the population standard deviation. Because of that, we end up with a lot more variability. Our capture rate is not what it needs to be. So we have to introduce this new distribution. The normal distribution is not going to work. So the new distribution is called the t distribution. And essentially, it looks exactly like the normal distribution. It's just more variability, more variability. So, and another thing that changes is the shape of the t distribution changes with something called the degrees of freedom. And the degrees of freedom, at least in this section, are calculated by the sample size minus 1. So you'll notice in this graph, as the degrees of freedom increase from 2 to 9 to the standard normal distribution. As the degrees of freedom increase, that means your sample size is increasing. And as the sample size increases, we have less variability. So as the degrees of freedom increase, the t distribution actually becomes more and more shaped like the normal distribution. So some facts about the t distribution: it's still a density curve, very same shape. It's spread out more variability, which I talked about. And as the degrees of freedom increase, the t density curve approaches the standard normal density curve. Okay. So we have to be able to find a critical value for the t distribution. And the way that we do that is we're going to use our calculator to do that based on the degrees of freedom and the confidence level. So I'm going to need to get that loaded up. Let me take a second and do that. All right, while that's loading, you can use a table. We're not going to use the table. Inverse t is what we're going to use. So you're going to put in the tail percentage and then the degrees of freedom. So it's under the second vars menu, inverse t. We're going to use it the same way we used inverse norm to calculate critical values. So say I have 95% confidence, that would leave 2.5% in each tail. And say my sample size was 30, then I'd have 29 degrees of freedom, 30 minus the 1, and I would calculate that value. So that's how you're going to do it. That's what it's talking about in the how to do it on the calculator here. So check your understanding. At this point, why don't you pause the video, try to do this on your calculator, and then come back and watch me go through it. So 96% confidence interval leaves 2% in each tail, 22 observations. So I would do a inverse t with 0.02 and 21 degrees of freedom. Oh, perfect. It puts it right on there. 99% confidence. So I would do inverse t of 0.005 with 70 degrees of freedom is here. So that's that skill. Next, conditions. Going to see a lot of similarities here. CVS, random condition, means that there was a random sample or a random experiment. We're not going to see experiments yet, so it's just going to be a random sample. That means the estimate is unbiased. It's centered at the true mean. 10% condition because we're sampling without replacement. The sample size is less than 10% of the population size. Because that's true, we can calculate the standard error. And then notice we do not have the large counts condition because we don't have a value for p or p hat. Like that wouldn't make sense. So we're using what's called the normal/large sample condition. Quantitative has 3 T's in it, so we need 3 10s. 30 is our magic number. Remember, categorical 1 T, 10, quantitative 3 T's, 10, 20, 30. So basically, the population is normally distributed, or your sample size is large enough that the central limit theorem is going to apply. Or we'll look at one more case where they give you the actual data. All right. Okay. Sampling from a normal population. No. All right. What we could do here is take a look at these 3 scenarios, and they say, can we calculate a critical T value? So your conditions have to be met in order for that to be the case. All right. Part A, random selection. Boom. 50. Boom. What else? Let me pause this real quick. All right, so we were talking about this idea here of the random sample. We have a random sample. Our sample size 50 is large enough. 50 is less than 10% of students from classes you take. That may be subjective depending on if you're at a university or not. We'll assume that's met, so that's good. Part B, we have, let's see, random sample, check. 20 is not bigger than 30. That's going to be an issue potentially. So if I look at this stem plot, this is skewed heavily to the left. So this is a problem. I have some severe skewness that I'm not going to have a sampling distribution that's approximately normal. So no, I could not calculate a critical T. For this third part, random sample check, 20 is not bigger than 30. So I'm going to have to look at the actual box plot here. I do have some skewness, but I don't have any outliers or really strong skewness, so I'm going to be okay there. So let's see. Okay, random sample. Okay, so I overlooked that part. 50 students was only from your classes and not from the high school, so that's not really a random sample. So that is an issue. This is very important here, this AP exam tip. I get asked this every year, like, what if the conditions aren't met? It will never give you, the AP will never give you a question where the conditions are not met and expect you to somehow construct the interval. They'll frame it in such a way to tell you the conditions are not met. So if you think they're not met, you've made a mistake. Constructing a confidence interval. So here's the actual structure we're going to use. Just as every confidence interval that we've done, it's going to be the point estimate plus or minus the margin of error. So for us, it's going to be the statistic, which is the sample mean. That's our point estimate, plus or minus this critical value times the standard error. This is technically the standard error because we're estimating. So this whole part of the confidence interval is called the margin of error. So it's the sample mean plus or minus the margin of error. This kind of talks through how to do one. That's another one. If you have the raw data, and the sample size is less than 30, you're going to have to create some kind of graphical display to check for skewness and outliers. I recommend doing a box plot because it will automatically show outliers. You don't have to do any thinking behind that. It can be easier to do a dot plot as well because that requires no calculator. So just a couple of options there. This is just going over calculator stuff. Okay. Calculate and interpret. This is the 4-step process. So I'm just going to verbally talk through the 4 steps. I doubt that it's going to show on the answer all 4 steps, but the state is going to be the parameter and context. So that's going to be, let's see, the true mean healing rate. Studying the healing of skin wounds measured at the rate. Okay. So it'd be mu equals the true mean healing rate of these skin wounds. That would be the state step. The plan would be for C, random sample of 18, check. For V, 18 is less than 10% of all newts, check. For S, they didn't tell me this population was normally distributed, so that's out. 18 is not greater than or equal to 30, so that's out. So I'd have to construct a dot plot or a box plot and look for strong skewness or outliers. And as long as I didn't see that, then I could conclude the sampling distribution is going to be approximately normal. So let's see what they did here. They do have state plan. All right, they did a histogram. That would be way too much work in my opinion. So large sample / normal condition. The histogram shows no strong skewness or outliers. Keep in mind, the conditions will always be met unless they explicitly tell you they're not. So you're like, oh, I have some skewness. It's okay. All right. The do step is going to be, you're going to have to find the sample mean from the calculator. So you plug all this data in, you run one variable statistics. That'll give you your sample mean and your sample standard deviation. As far as the interval goes, the critical value, I do inverse t of 0.025 with 17 degrees of freedom. Let me scroll down so we can see. So there's your sample mean, plus or minus your critical value, times your sample standard deviation. So this 25 and 8 come from doing one variable stats in list 1. So add and subtract the margin of error. Conclusion is going to be the same. We're 95% confident that the interval from this to this, now we have units, micrometers per hour, captures the true mean healing time for newts. So there's your 4-step process. You want to split that paper up and you want to make sure you have all 4 of those. The one thing that I don't see in here, it is in here. At the end of the plan step, you have to name this procedure. This is called a one sample t interval. It's not one proportion. We don't have proportions. We're using the t distribution, not the z. So that's why it's a t interval. All right, moving on. This is no longer part of the AP curriculum, so you don't need to do that. And summary. So we use the t distribution because we don't know the population standard deviation. We have that extra variability because we're estimating 2 things. So we have this whole new distribution. It has n-1 degrees of freedom. We check our 3 conditions. We construct a 4-step process for the one sample t interval, and you don't have to do this sample size part. So I hope that was helpful. Have a good day.